Dr. Ed Laws is going to give our talk today, and we all know him. He's been a mainstay of the faculty since the early 2000s here, when he came over from Hawaii, right? Yeah. And he's been instrumental in teaching some of our largest classes in the College of the Coastal Environment. He also has done quite a number of things outside the university, like tutoring inmates in prisons, and lots of different projects that he's engaged the community with. And one thing that is kind of putting a cap on all of his accomplishments is he is going to be announced as one of the Distinguished Research Masters for this year, which is one of the most prestigious awards you can get at LSU, kind of a lifetime career achievement award. So.
Obviously, I'm going to talk about climate change. Let's see if this guy's working. Yes, it is. Okay. Bottom line here is that what's happening now with respect to the climate is similar in many ways to what happened about 250 million years ago, the so-called PT extinction in the Permian Triassic extinction, which was the greatest extinction of all time, as best we can tell from the geological record. And as I go through this, I mean, not only is what's happening now similar, it's arguably worse. And so we have some real reasons to be concerned about what's going on. Okay, so first of all, yeah, the climate of the Earth has been changing. We're in an ice age right now. That's not the norm. Fact is, over the time frame of the Earth where we have a geological record, a fossil record, the climate has generally been warmer than it is now, which is interesting considering all the concern about global warming. On the geological time scale, the two things that drive the change in climate are the greenhouse gases, which of course we can relate to, and then the solar constant, which turns out not to be constant. And it's changing very slowly, and I'll get into that. Okay, so photosynthesis takes CO2 out of the atmosphere. That should not be surprising to anybody. Then there's a process called weathering, which I'll explain briefly. That's reaction between carbon dioxide, water, and rocks. That also takes CO2 out of the atmosphere. So you have two, on a geologic time frame, you have two mechanisms to take CO2 out of the atmosphere, photosynthesis and weathering. And you have one mechanism to put it back on that kind of a time frame, and that's volcanoes. And you usually don't think of volcanoes as being our friend, but that's actually very important in regulating the climate. Okay, so those are the principal mechanisms involved in that kind of time scale. Okay, what happened at the PT extinction? There's really good evidence of this. There was a very long, roughly million-year-long series of volcanic eruptions in what is now Siberia, and those volcanic eruptions put a lot of CO2 up into the atmosphere. Again, on the geologic time frame, it's volcanoes that put CO2 into the atmosphere. The CO2 concentration went way up, and I'll look at exactly where we think it went. So there was a warming, and there was roughly a 90% loss of species in the ocean associated with that. And why would volcanoes in Siberia cause extinction of species in the ocean? And the answer is climate change. Temperature went up. Okay, the important point here is that most of the ocean is in the dark as far as photosynthesis is concerned. Sunlight does not penetrate more than roughly 150 meters into the ocean in sufficient amounts to support photosynthesis. So you don't have any biological mechanism, and the ocean is over 3,000 meters deep on average. You don't have any mechanism, most of the ocean, to put oxygen into the water, only in the surface waters. So the only way you can get oxygen throughout the ocean is by physics, by sinking surface water that is saturated with oxygen. So right now, this is called the thermohaline circulation of the ocean. Right now, there are basically two places where deep and bottom water is formed in the ocean. One is off the continent of Antarctica in the wintertime in the southern hemisphere. You're forming sea ice, so you're at the freezing point of the water. And as you form the sea ice, most of the salt is left behind in the water. So the water is at the freezing point, it's getting saltier and saltier. That water actually sinks all the way to the bottom. In the North Atlantic, during the wintertime in the northern hemisphere, you also sink water just because it's cold. It does not go all the way to the bottom. It does go to several thousand meters depth. And that's called North Atlantic deep water. So right now, there are these two places where you form deep and bottom water. That's it. And once that water sinks, it goes on a very long journey, roughly 500 to 1,000 years. That oxygen has to last for 500 to 1,000 years. So you can see how this is sensitive. If you slow down the thermohaline circulation of the ocean, or literally stop it, you're in big trouble. And that's apparently what happened. There's good geological evidence for this 250 million years ago, because the climate warmed. Right? And as I go through this, I'll point out that where the climate warms the most is unfortunately at high latitudes, which is exactly where we want to sink this water. Right? So very likely the thermohaline circulation of the ocean was seriously disrupted. The ocean went anoxic. There's good geological evidence for that, and a lot of species went extinct. Okay. So, fine. How high did the CO2 concentrations go 250 million years ago? This is bad news. It went to about where we think, it's an easy calculation to do, where if we burn all the fossil fuels, the CO2 concentrations in the atmosphere will go to about 2,000 parts per million. Right now they're a bit. The evidence is that 250 million years ago, the CO2 concentrations went to about 2,000 parts per million. And that led to the greatest extinction of all time. So this is obviously a reason to be concerned. Okay. Now, I said it could be worse now than in the past, because the continents right now are not where they were 250 million years ago, right? The continents have been slowly moving around. So we have not a unique, but a different situation in the northern hemisphere, with the Arctic Ocean surrounded by continents, and Greenland sitting there with, in round numbers, 1,000 meters of ice sitting on Greenland. Okay, we are in the process of melting ice on the Arctic Ocean. The ice on the Arctic Ocean is not 1,000 meters. It's not 1,000 meters. It's a meter or two, a few meters. That's why the polar bears have to go do whatever they do during the summertime, because the ice won't support it. And the fact is, the Arctic Ocean is in the process of thawing out during the summertime. It's becoming free of ice. Okay. Why is that important? Because snow and ice reflect incoming solar radiation. It's called the albedo, the reflectivity. Snow and ice reflect almost all incoming solar radiation. If you melt that snow and ice and you have open ocean water, it's going to absorb almost incoming solar radiation. So we're now in the process of changing the albedo of the Arctic Ocean. This is going to dramatically increase temperatures at high latitudes in the northern hemisphere, because the Arctic Ocean, instead of reflecting incoming solar radiation, is going to be absorbing it. And then you've got 1,000 meters of ice sitting on Greenland. Now you start seriously melting the ice on Greenland. Okay. And when you melt the ice on Greenland, a lot of fresh water flows into the North Atlantic. It's very hard, to say the least, to sink fresh water through salt water. You can't. Right? So we're warming up things dramatically at high latitudes in the northern hemisphere. Plus, we're going to start melting the ice of Greenland and dumping lots of fresh water into the North Atlantic. That's going to seriously disrupt the thermohaline circulation. Okay. Now, I said here, Mother Nature will eventually come to the rescue. The ocean will take up virtually all the CO2 we're putting up there right now. there's about 50 times more inorganic carbon in the ocean in the form of bicarbonate than there is CO2 in the atmosphere. And that it takes 10 or 20,000 years for the whole system to equilibrate. So, if you're willing to wait, to a geologist, 10,000 years is nothing. True. But, okay, Mother Nature will come to the rescue, but you're looking at 10 or 20,000 years, not a couple of decades. Okay. I just wanted to make this point. I was talking to the students in 1126 about this. They still don't get this. Why do CO2 concentrations go up and down seasonally? And this has nothing to do with volcanoes or weather. It has to do with photosynthesis and respiration. So these are the average concentrations of CO2 recorded at Mauna Loa over the last roughly 20 years. You can see, CO2 concentrations go down, starting around the middle of spring until the end of summer when you've got photosynthesis is ahead of respiration, so it's taking CO2 out of the atmosphere. And then you go into fall and winter, the CO2 concentrations go up because of respiration, not because of volcanoes. So this is somewhat different. I mean, photosynthesis is involved, but it's not volcanoes, it's not weather. Okay. So this is the weathering. If you talk to geologists, this is their, how does CO2 get taken out of the atmosphere? Weathering and photosynthesis. So this is the weathering. Weathering is a reaction between carbon dioxide and water, you can see on the left there, and rocks. And the CaSiO3 is just a shorthand for a rock. It's a silicate rock. Okay? So the CO2 is going to react with the water, you're going to get carbonic acid, which, as I tell the students in 1126, it's what's in beer, it's what's in wine, it's what's in Coca-Cola, right? It's carbonic acid, it's a weak acid. Okay, but Mother Nature's not in a hurry. So weak acid is going to dissolve the rocks. You can imagine dissolving a rock by pouring Coke on it. But that's what Mother Nature does. It's a slow process. Mother Nature's not in a hurry. Rocks dissolve. Down in the river goes the CO2, now in the form of bicarbonate, primarily. Goes into the ocean, and then you have biological processes. Form calcium carbonate, goes into the sediments. Okay? So that's what that diagram is showing. Okay? So the weathering is reaction between CO2, water, and rocks. It takes the CO2 out of the atmosphere, eventually buries it at the bottom of the ocean. So that, you folks know what photosynthesis is. You've got these two mechanisms on the geologic timescale, photosynthesis and weathering, that can take CO2 out. And if you didn't have volcanoes, there's no mechanism to put it back. Okay, big problem. Okay, now I just want to make this point about volcanoes. There are volcanoes and there are volcanoes. Some volcanoes are very gassy. Some are not. Okay. So you see a picture here, this idiot in the lower left. I don't recommend getting this close to molten lava. But that's a lava flow in the Hawaiian Islands. And the volcanoes in the Hawaiian Islands are not particularly gassy. I mean, there's some CO2, but not much. So, I mean, they're very active, but those volcanoes don't put much CO2 in the atmosphere. Then you see Mount St. Helens before and after. See, that was a very gassy eruption, blew the top off Mount St. Helens, right? So you have these two extremes where the lava just comes oozing out and there's a little bit of CO2. You have the very gassy reactions and then everything in between. And so on a geologic timescale, it's the volcanoes, particularly ones like this, that put the CO2 into the atmosphere. And photosynthesis and weathering are going to take it out. Okay, now this is a model. It's called GeoCarp. The person who put this model together is Bob Berner at Yale. And he's looking at the CO2 concentrations in the atmosphere over what's called Phanerozoic time. Phanerozoic is a eon of time. It lasts roughly 570 million years. And why is he looking at that? Because that's when we have a fossil record. Right? You start getting complex organisms at the beginning of that time frame. So the geologists as something to work with. They can infer, when you look at isotope ratios and so forth, but you have a good geological record over that time frame. And so what you notice there, it says RCO2. That is the ratio. That is the ratio of CO2 concentration in the atmosphere in times past to the present. Right? So if you come over all the way to the right-hand side, there's 1. Right? So what Berner is telling you is that if you go back 570 million years, you had 15 or 20 times as much CO2 in the atmosphere as you do now. And you say, my God, it must have been hotter than hell. No, it wasn't much different than it. I mean, it was warm, but it wasn't that much warmer. And the reason is the solar constant. Okay? The sun is not constant. So, right, the sun is running a fusion reaction, right? And it's converting mass into energy. What holds the sun together? And so the people are trying to do fusion reactions right now, right, and control them and generate electricity. How are they going to hold this thing together? With a huge magnetic field, right? Magnetic field. The magnetic field is not holding the sun together, right? Why doesn't the sun just blow up? Gravity, right? The sun is huge. It's got a huge gravitational force, and gravity is what holds the sun together. Okay, now comes the problem. As you go through millions and millions of years, the sun is converting mass into energy, which means its gravitational pulls become less. So you can look at other stars. The sun is so-called main sequence star. You can look at stars like the sun and see what they do over their lifetime. Right? And the answer is they get bigger, right? Because the force of gravity is gradually becoming less and less. So if you go back 570 million years, or even before that, when the solar system was formed, the sun over that time frame, billions of years, has been gradually getting bigger. So if you go back 570 million years, there wasn't as much sunlight hitting the Earth, right? Because the sun was small. And so convenient, to say the least. So you've got 15 or 20 times as much CO2 in the atmosphere at the start of the Phanerozoic, but the solar constant was less than it is now. And so if you put those two together, it doesn't change the temperature very much. I mean, you might think this is terrible, but no. Okay. So this again is Berner's model, but what he's looking at there, the solid curve, is according to the model, the temperature, and you're just looking at 0 is the present temperature, just relative to the present temperature. Right? So you go back 570 million years. You can see that over that time frame, most of that curve is above 0. Right? So the climate on the Earth has been warmer than it is now during most of this time, not all the time, but most of the time. But it's, it hasn't been off the charts, maybe 5 or 6 degrees warmer. Okay. Now the dashed line there is what would happen, according to the model, what would happen to the temperature if you put the CO2 concentrations, what it is right now, and held it constant going back in time. So you would have 400 parts per million CO2 in the atmosphere 570 million years ago. You see what the temperature would be, 10, 15 degrees lower. Right? So it's just convenient as the dickens. Well, there weren't any humans back then, so who cares? But it is a fact that the temperature of the Earth hasn't changed all that much over geologic time, even though the amount of CO2 in the atmosphere has changed dramatically. You go back in time, you're looking at 15 or 20 times as much CO2. Okay, but that's okay. Now we can look forward. Say, okay, what's going to happen? The sun is going to continue to get bigger and bigger, right? This is bad news, depending on how easily turned off you are. But the sun will, if you look at other main sequence stars and see what they do, eventually they turn into what are called red giants. They get really big, right? Because the force of gravity is pulling them together very effectively. And that's what will happen to the sun. Okay. And so when the sun turns into a, quote, red giant, it will literally swallow up Mercury and Venus. We don't think it will swallow up the Earth, but it won't matter, because by the time the sun gets that big, all life on Earth will be gone, the oceans will boil away into outer space. Right? And the time frame for that is several billion years. So I got this figure off the internet, and this is This is the sun now. This is the sun 5 billion years. It's crazy. So that's what lies ahead. But don't worry about it. It's billions of years into the future. See, this has been going on, going back in time. I mean, obviously not this extreme, but the sun was smaller 570 million years ago. And that is conveniently why the temperature hasn't changed all that much. Okay. So this is I got this again off the internet. It's showing you the temperature and the CO2 concentration in the atmosphere going back to the Cambrian, beginning of Phanerozoic time. So the black curve there is the CO2 concentration. So now they're actually showing you, or sorry, the black curve is the temperature, right? The blue curve is the, no, I'm sorry, the black curve is the CO2 concentration, and the blue curve is the temperature. Okay. So you can see that going back to the beginning of Phanerozoic time, the CO2 concentration is much higher, and it came down steadily for about, until you get to about 300 million years ago. Now, if you read Werner's explanation of this, does that mean, more volcanic eruption, less volcanic eruption, what's going on? Photosynthesis. Okay. So the point is, you go back in time and you look where life first evolved. It had to evolve in the ocean. And the reason is, early on there was no oxygen in the atmosphere. So there was no UV shield, and no ozone or O2 up there to block the ultraviolet radiation. So it was impossible to have life on land. So life at first evolved in the ocean because water is a good absorber of ultraviolet radiation. So you start to get photosynthetic organisms that start producing oxygen. Right? Does the oxygen come out in the air? No. The oxygen starts reacting with things in the ocean, particularly sulfur and iron. Now the ocean is full of sulfate, which reflects how that played out. And basically all the iron precipitated out. Right? So if you go in the ocean now, you see there's very little iron. And most of the iron ores that we exploit today go back several billion years to this called the rusting of the ocean. So there's a long period of time there where oxygen was being produced in the ocean, but it wasn't getting out into the atmosphere. Finally started getting up 600, 550 million years ago, whatever. You start getting enough oxygen in the atmosphere that you have a block on the UV. Then you start getting plants and animals on land. So what Werner says is this drawdown of the CO2 concentration between the start of the Phanerozoic and roughly 300 million years ago reflects what he calls the rise of vascular land plants. Okay, the rise of photosynthetic organisms on the land. Now, if you want to know what a vascular land plant is, it's just about any plant you care to name, except mosses and a few other oddballs. But basically, because there was finally a block on the UV, plants started to evolve on the land, taking up CO2, the CO2 concentrations come down. Okay, and then you can, if you look at the temperature curve there, the blue curve, you can see, yeah, during most of Phanerozoic time, the temperature was warmer than it is now. So if you go back about 250 million years ago, that's going to be the PT extinction. The PT extinction is right there at the dividing line between the Permian and the Triassic. And you look at the temperature there and you look at the CO2 concentrations and you compare them to what they are now. Very similar. Right? This is the only time during the Phanerozoic when the temperature and the CO2 concentrations were about what they are now. Okay? And then you see the CO2 concentration suddenly goes up. And it goes up to about 2,000 parts per million. And the temperature goes up. Well, fine, because it's a greenhouse, right? Temperature goes up abruptly, the CO2 concentration goes up abruptly about 250 million years ago. This is the biggest extinction of all time. 2,000 parts per million. That did it. Okay. But there were no people on the Earth, obviously, 250 million years ago. So what caused the CO2 concentration to go up? Volcanoes. Right? That's it. Right? Now, this is a one-page paper in Nature. It's been widely cited. It's a model by Caldera and Wickett. And actually, this paper was mainly concerned with ocean acidification, which you can see the bottom of this is what's happening to the pH in the ocean. But okay, let's look at the top. Those are emissions of carbon dioxide. If you integrate under that curve, you get exactly what people estimate to be the recoverable fossil fuels. So Caldera and Wickman just said, okay, let's assume that human beings burn all the fossil fuels that we know about or are exploited over a time frame of about 500 years. So that's that curve, and then you run out by the year 2500, you run out of fossil fuels. Okay. And then you look at what happens to the CO2 concentration in the atmosphere. Where does it go? About 2,000 parts per million. Almost exactly where it went with the PT extinction. And then you see it very slowly comes down. That's because the ocean is taking it up. And if you're willing to wait 10 or 20,000 years, the ocean will take it all up. So here by the year 3000, you've still got 1,500 parts per million CO2. That's the problem. So by burning, if you burn all the fossil fuels over a time frame of 500 years, the CO2 concentration in the atmosphere goes to 2,000 parts per million, which is exactly what caused the P2 extinction. Not good news. Right? So that's the problem I want to hit on. Right? Now, okay, so what happened to P2 extinction? You can see 90% marine species, 60% animal species, blah, blah, blah. How do we know this? Fossil record, right? And the best fossils turn out there in China, this place in southern China, so I just put that in there. That's where a lot of the evidence for this comes from. Because those sediments, well, you can't go to any place in the ocean and find sediments that are 250 million years old, right? Because of subduction, right? They've been subducted, but these have been uplifted. So you have the geological evidence there of the mass extinction. Okay, so what caused all this CO2 to go up in the atmosphere? Volcanic eruptions, right? And what they're called is the Siberian traps, which I'm not going to into that. It's a Swedish word or something like that. Right? 1 million year long, roughly, series of volcanic eruptions in what is now Siberia. You can see millions of cubic kilometers of lava flowed out, and you can go there now. This is it. I don't know what language this is. I got this off the internet. But this area that's outlined there is the area where these volcanic eruptions occur. So it's a wide area of Siberia, 1 million years ago, what's going on. And if you go there now, this is an example. This is the basalt that came out 250 million years ago. It's 2,000 meters thick. That's a lot of basalt, right? And so these volcanic eruptions introduce lots of CO2 into the atmosphere. Now, if you talk to the geologists, there's more here because it seems that overlying some of this molten rock, the magma chamber, or deposits of coal. And so we can imagine when the molten rock came out, the coal just got vaporized. So these volcanic eruptions, yes, they introduced a lot of CO2 into the atmosphere, right? But there were other factors involved. Okay, so 1 million year long series of volcanic eruptions. Lots of CO2 goes up there, roughly 2,000 parts per million. And then you have the biggest extinction of all time. Okay. This is a thermal circulation in the ocean now. Now, one thing you want to remember is the continents are not now where they were. And I'll get into that, but the position of the continent is different. And the position of the continents now is arguably especially troublesome. So you have this one area off the Antarctic continent where you form bottom water. It just says deep water, but it actually goes all the way to the bottom because you're at the freezing point. You're adding salt, so that water goes all the way to the bottom. The blue arrows, or the blue, whatever you want to call it, conduits. Those are the bottom curves. So then it goes, once it sinks and it's loaded with oxygen. And if you know anything about the solubility of oxygen, the colder the water, the more the oxygen is going to be in it. So this water is loaded with oxygen when it sinks. But it's down there for 500 to 1,000 years. So that oxygen has to last a long time. And the other place, as I said, is in the North Atlantic. And you say, well, what about the North Pacific? That's a salinity problem. Right? The surface water of the North Pacific is not salty enough to sink very far. nothing like the North Atlantic. So you have these two places where you form deep in water, bottom water effectively. This is what you do not want to interfere with, because that's what put oxygen into the bottom waters of the ocean. There's no photosynthesis going on below a depth of 100, 150 meters. Okay, so is there evidence? Is there geological evidence for anoxia? Yes. And I cited a couple of papers here. One PNAS, the other is global and planetary change, but there's plenty of geological evidence that yes, the oceans went anoxic 251 years ago, and that's almost certainly what caused the extinction of 90% of marine species. Okay. Why does the temperature go up most at high latitudes? It's not because there's more CO2. It's because there's less water vapor. So CO2 and H2O compete with one another to absorb infrared radiation. And anyone who's been here during the summertime knows this air is full of water vapor. Right? So you go to low latitudes, you have lots of water vapor that's competing with the CO2. So the CO2 is comparatively less important as a greenhouse gas at low latitudes than it is at high latitudes, because when you go to high latitudes, the air is burned dry. And then CO2 is your dominant greenhouse gas. So that's just a picture showing you the distribution of water vapor. Okay. Now, this is a projection of the Intergovernmental Panel on Climate Change. They're looking at what's going to happen to the temperatures by the end of this century, year 2100. And you see, if you look at the color scale there, you see the temperatures go up more at high latitudes than they do at low latitudes. However, the difference is far less dramatic in the southern hemisphere than it is in the northern hemisphere. Why? Because Antarctica is covered with several thousand meters of ice, which reflects incoming solar radiation. So God forbid that we melt the ice on Antarctica. So yeah, the temperature is going to go up more at high latitudes in the southern hemisphere than it is at the equator, but it's not really dramatic. Where the temperature is really going off the charts is the Arctic Ocean, right? Why? Because we're going to melt the ice on the Arctic Ocean. It's just a couple meters of ice. And then you completely change the albedo of the Arctic Ocean, and you start absorbing instead of reflecting incoming solar radiation. So, they put this in a computer model. That's what it says. The temperature is going to go up like 10, maybe more than 10 degrees Celsius at high latitudes in the northern hemisphere. I can see that this is going to seriously interfere with the sinking of deep water in the North Atlantic. Right? So this is a picture, NASA, right? Your tax dollars at work. This is just the last September. So the yellow curve there you see is the historic extent of sea ice in the Arctic Ocean at the end of summer. Right? This is where the polar bears have to get out of there. And you can see that at the end of summer last 2024, there's a lot less ice on the Arctic Ocean than there has been historically. Right? And that's because the temperature is going up. Right? And it doesn't take a whole lot to melt a meter of ice. Right? We're not talking about 1,000 meters of ice. Okay, so the Arctic is in the process of thawing out. Who cares what happens in the winter? There's no sunlight, it doesn't matter. It's in the summertime that you want to absorb or not, incoming solar radiation. Okay, so this is what's been happening to the extent of snow and ice on the Arctic Ocean at the end of summer. Going back to 1980, you see steadily coming down. So the folks who work with these computer models say that by roughly 2050, the Arctic Ocean will be free of ice at the end of summer. So that the albedo is going to totally change. Now, if you look at that not too closely, I say, yeah, okay, it's going down. Well, okay, here's a paper that just came out fairly recently, 2023. It's basically the same data, but the point they're making is that if you go up to about 2005, look at what happens after 2005, probably to 2007. Okay, the decline has almost stopped, right? I mean, it's a little bit. So, is this God coming to the rescue, or what? Why is the extent of sea ice suddenly stopped decreasing dramatically during the last 10 or 15 years? So what they say is, you can see, fluctuating Atlantic inflows modulate Arctic Atlantification. Okay? This has to do with circulation of the atmosphere, and you get into all that meteorology. But the flows of surface water into and out of the Arctic Ocean have changed, right? And that has slowed down dramatically this process. We don't have any reason to think that this is some kind of long-term halt on melting the ice on the Arctic Ocean. Okay. So the projection is that by the middle of this century, the Arctic Ocean will be free of ice, and then the temperature goes up to 10 or 15 degrees. Okay. So that's bad if you're trying to sink water, right? But there's more bad news. Okay. There's the Arctic. All that albedo is going to change. Okay. So here's the other problem. This is it's an editorial comment by this fellow Stefan Rahmstorff in Germany, and what he's looking at is the impact of the ice on Greenland melting and the fresh water flowing into the Arctic Ocean. Never mind the temperature, right? You can't sink fresh water through salt water. Okay, so he puts this in a computer model. There's the currents. Okay, so this is the model, and so you have NADW, it's North Atlantic Deep Water Formation, and you have freshwater force. Okay. Now the SV there is spheroids, and it's an oceanographic term, and it's, if you want to know, it's 1 million cubic meters per second. So that's what we're talking about. Spheroids. So if you look at the solid curve there, as you add fresh water to the Arctic Ocean, the rate of North Atlantic deep water formation slows. And then, let's see if I can get this to work. Yeah, okay. So you get to this point, it's slowing, it stops. You stop forming North Atlantic deep water. Okay. And you can imagine why that might happen. And he's not even looking at temperature effects, he's just looking at fresh water. And you come all the way down here, now you're not forming any North Atlantic deep water. But now there's a real problem. You've got what's called a regime shift. Okay? And in order to turn on the formation of North Atlantic deep water, you have to bring the force all the way back to here, to 0. And then you jump up. That's the regime shift. Okay? Now, there's a 0.1 spheroids. Okay? So how much water, if we melt the ice, what's the rate of freshwater flow into the North Atlantic? Okay. So this is how much water ice, right? There isn't Greenland. Now we have to say, okay, how long do we think it's going to take to melt all that ice? And the answer is, we don't know. Okay, there's a couple scenarios. One is the ice just melts and drip, goes into the North Atlantic. The other is that the ice melts and the fresh water flows down through cracks in the ice and lubricates the interface between the ice and the rock, and big hunks of ice just slough off. And we have no historical record of this sort of thing going on, so we're just guessing that the time frame that people mention is 500 to 1,000 years. Okay, so I just said, okay, let's assume that it takes 1,000 years to melt all the ice. And all that fresh water goes into the Northern Atlantic. You're looking at, on average, 0.08 spheroids. Okay, so you come over here and say, we're saved, right? It's not going to turn to the north. That's stupid, right? Why? Because there's no reason to think that the flow of fresh water would be constant for 1,000 years. Right? At the start, it's going to be drip, 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 and at the end, it's going to be drip, 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 and in between, there's going to be a lot of fresh water flowing into the North Atlantic. So it's certainly possible that in addition to ramping up the temperature by 10 or 15 degrees in the high latitudes in the Northern Hemisphere, we're also going to have lots of fresh water going in here, which is at best slow down the formation of North Atlantic deep water, and worse shut it off when we go into a regime shift. And then we have to go all the way back to 0 freshwater forcing. Okay, so we've got two things going on here that seriously interfere with the thermal inlet circulation of the ocean. One is the temperature's going up at high latitudes, and the other is in the North Atlantic, you've got a lot of fresh water going in because you're melting the ice in Greenland. Now, of course, the other thing with melting the ice in Greenland is sea level rise. Right? Now, I just wanted to point this out. This is where we think the continents were 250 million years ago. There was a giant continent. And you see, you don't have a situation like the North Atlantic here. You don't have a relatively isolated body of water sitting either in the North or South Pole. Still, 90% of marine species went extinct at the PT extinction. So, and there's ample evidence of anoxia in the ocean. So even if you didn't have a situation like the North Atlantic or the Arctic Ocean, you still wiped out 90% of marine species, very likely from anoxia, which means you shut down the thermal alien circulation. Okay, well, I'm just going to show you some slides here. What happens when you raise sea level by 7 meters? And these are all made by students of UNA Lab. So this is what happens in Louisiana. Hey, we're on dry land, right? We're in Baton Rouge. But you can see the whole is so delta above it, and that's a 7 meter rise.
Sure.
Now this does not allow for thermal expansion of the ocean, right? Which is going to happen. That's just 7 meters melting the ice in Greenland. And I gave a talk somewhat like this in China a couple of years ago. So I showed them what's going to happen to the Chinese coast of Shanghai. Right? The whole place goes underwater. This is the Bohai Sea. Again. And then I'm scheduled to give a talk in Nigeria. I'm not actually going there. I'm remotely, but this is, so I had this Nina's postdoc. He made this map for me, and this shows you what happens to the coastline of Nigeria. And you better believe there's a lot of people. I mean, go to any place, a coastal environment, New York City, 7 meter rise in sea level is a serious problem. Now that's, people talk about that more than shutting down the thermal alien circulation in the ocean. I don't see a lot of discussion of that issue. And see, it's part of the problem. It's not going to happen in your lifetime or mine, God forbid. We're looking at hundreds of years down the line. You've got to melt the ice on Greenland. Okay, so this is a more immediate concern here. Okay, so in the fall semester, we had a fellow come here named Andrew Jones, and he has this computer program, NROS. So this is supposed to simulate, it's a kind of a game you can play, how to deal with climate change. And so if you look at your options down here, there are various things that you can do to try to prevent the temperature from rising. The default, if you don't do anything, is 3.3 Celsius by the end of this century. Right? And so the students were told, okay, you guys figure out how you can keep this temperature rise below 1.5 Celsius. And it turns out you can if you play around with these things, use energy more efficiently, and so forth and so on. Okay, so Andrew gave a talk right here in the auditorium about this. And if you go on the internet, you can see that this software is being marketed all over the world. So at dinner that night, I asked Andrew Jones, do you have melting of the Arctic Ocean in this model? No. Come on. I think the problem is, well, if you look at this graph, he only goes to the year 2100. Right? So the ice on Greenland is not going to melt off by the year 2100. But the Arctic Ocean, very likely, will be free of ice by the end of summer, maybe 2050. So the temperature is going to go up a lot. It doesn't have this in the model. I think it's a bit misleading, but it gives you the impression that if you tinker with these things, you can get the situation under control. I think it's going to take more than tinkering to solve this problem. And the reason is you burn all the fossil fuels. In 500 years, the CO2 is going to 2,000 parts per million. And because it stays up there for long, it takes a long time for the ocean to soak it up, right? Which means it doesn't really matter very much whether you burn all the fossil fuels in 500 years or 600 years. The net result with the CO2 in the atmosphere is going to be about the same. So I wasn't real happy with that. And that's just to remind you, this is what the Intergovernmental Panel on Climate Change is saying is going to happen by the end of this century because we're melting the ice of the Arctic Ocean. Okay. Now eventually, Mother Nature comes to the rescue. CO2 goes into the ocean. Finally, it gets down to the bottom of the ocean, reacts with sediments at the bottom of the ocean, and you form bicarbonate. Okay? And the time frame for this is 10 to 20,000 years. But that will eventually happen. And I just want to point this out. It's kind of provocative. Look at, oops. Not sure what fast. Okay. This is the carbon, where the carbon is. See, this is the carbon in the atmosphere, and this is the carbon in the ocean. So there's about 50 times as much inorganic carbon as most of the carbon. So that's going to equilibrate, and that's why most of it's going to go in the ocean. But if you look at where most of the carbon is, buried in sediments, about 80, if you look at, about 80% of that is carbonate rocks, and the rest is organic matter. Okay? But that's, this reflects what's been going on over geologic time. We've been burying carbon, right? And that's why the CO2 concentrations have been coming down. Okay? So, reducing, they say, oh, we have to cut back on CO2 emissions. I think we have to stop burning fossil fuels. We need some of them in the ground. Because it doesn't matter, if you just slow it down, it's not going to be all that helpful. Right? Now, I don't know if any of you read any of Jared Diamond's works, but he does have this one book called Collapse, where he looks at how human societies fail, they collapse. And you can read this. People living in fragile and difficult environments, adopting solutions that were brilliantly successful in the short run, but failed in the long run. Now, what Diamond means by short term is maybe centuries, right? So you look at things that people do, they're trying to deal with whatever, and they come up with solutions that work for a long time, maybe longer than a human lifetime. But eventually they're doomed to fail. Okay, so I don't think that making more efficient use of fossil fuels is the answer. I think we just have to flat out stop using them. And so Diamond loves to make a list. And so here, why do human societies fail? They fail anticipated problem. Well, if all we're concerned about is what happens in the next 100 years, we're kind of missing the boat here. It's happened slowly, right? Failure to try to solve the problem, and realistically, what's the solution? You have to leave the fossil fuels in the ground. So, I gave this talk several years ago to some students in the LSU Honors College. I gave 2 talks about climate change. And I went through this in the first talk. So the student, this honor student comes up to me, and this is what he said to me. Okay. So, got to get out there and do something about it. I think it's not like we have to do something tomorrow, but we can't go 500 years and burn all the fossil fuels, or 600 years or 700 years. Burning all the fossil fuels is going to create a problem. It's going to go to 2,000 parts per million, or thereabouts, and then you're looking at what happened at the BT extinction. Okay, I'll stop there. Any questions?